I'm going to go over some basics of NumPy arrays that you should remember from previous courses. Of course, what we're going to do is first of all start with the necessary commands. I'm going to start with the matplotlib magic command. It's not a particularly brilliant way of referring to it. Essentially, this sets up matplotlib to plot within the notebook. There are other options that you can explore, and I'll show you that later. We're then going to import NumPy, and remember that we rename it as NP. And we're also going to import matplotlib, the pyplot part of it, or the pyplot module, and we're going to rename that as PLT. I'm not going to go into huge amounts of detail on pyplot in this video, but it's useful to have it available. We'll talk about it later in another one. Now, the whole of this computational physics course is going to rely on NumPy arrays, on creating them and on operating on them, because this is the most efficient way of working. And so the first thing you need to do is to remember how to create NumPy arrays. There's a variety of commands. Maybe the simplest is as follows. So we might say A is equal to np.zeros of 5. Now, what's that going to give us? Well, we could just run it. So let's try doing that. So I'm going to run it by doing Shift and Enter. That's run. It hasn't shown us anything. So let's now print A. Okay, and you can see that we've got a one-dimensional array with zeros in it. Notice that these are 0 point. Okay, so these are floating point types. It's important to remember that. Let's come back and think about other ways we can work out how commands work. So you'll notice I've put the cursor inside the brackets of the function, and if I do Shift and Tab at this point, it gives me the doc string for the function. So it tells me what's happening here. So you see that it gives us the arguments you can give it and a brief comment, return a new array of given shape and type filled with zeros. There's a plus here. If you hit that plus, you get a larger window and it gives you more detail that can be read through. This Shift Tab help function is incredibly helpful, and it's something you should get used to doing all the time. Now let's assume that we want to make a 2D array, let's say a 5x5 array. You might think that you can do the following. A is equal to np.zeros of 5, 5. Let's try running that. And you see that we now get an error. You can see that the error is indicated by this set of lines. So this is actually an arrow pointing to the line where the error is. That's here. And it says cannot interpret 5 as a data type. So let's come back up to this command here and do Shift Tab again. And you'll see that actually we've made a mistake. We've given the first argument is actually the shape, but we've assumed that we can give as many parts to the shape of the array as we want here. And that's a mistake. I'll show you how to correct that in a moment. What's happened is NumPy has quite correctly interpreted our second argument, the second 5 here, as being a data type, as if we're trying to tell it to make an integer or a floating point or something like this. 5 doesn't correspond to any kind of data type, so it throws up an error. Okay, so let's think about ways that we can fix this. What I'm actually going to do is I'm going to define a variable called shape. And initially I'm going to set it to be just 5, so it's just an integer. And now if I pass that variable shape to A, and actually I'm going to put the print A in the same cell so that we can just run that and see the result, you'll see that we get what we had before. I'm just going to delete that cell below. We don't need that. Now, how do I specify a 5x5 array? Well, what we want to do is we want to give it a setup like this. So you put the 2 elements that you want in there. If I've done that and I now run it, you see that I have a 5x5 array. And of course I can change that to a 5x2 array, or indeed a 2x5 array, and you should note what the differences there are. You've got 2 rows of 5 columns in this case. When we set it the other way around, 5, 2, then we have 5 rows each of 2 columns. And of course, there's nothing to stop you from putting that kind of bracket in here in the argument A, so we get the same result. But I think perhaps it's just a little bit clearer to see what happens by putting the shape in there. So that's the numpy.zeros. You can do something very similar with a numpy.ones. Let me just do that here. I'm not going to bother assigning it to anything. The other thing that you can do, and this maybe is interesting just for the moment, is to, let's say, b is equal to numpy.ones like A. Now, what does this mean? This means I want to create an array with the same shape as A, but filled with ones instead of zeros. And so let's just check that that works. And if I put print b there, we can see that we've got that. So these are all the kinds of arrays that you're going to need to be very familiar with, you're going to need to be happy with. The other useful array that you might like to think about here is numpy.I. This is a simple way of creating an identity matrix. So capital I it is there. And when you run that, you can see you get in this case, a 4x4 matrix with ones down the diagonal. You can actually specify another argument here, which is called k, which shifts the location of the diagonal. So if I put k equal to 1 here, you'll see that we've shifted the main diagonal up 1. You can imagine if I put k equal -1, it shifts it down 1. If you want to create an array filled with the same value, you can of course just do that value multiplied by numpy.ones. There's also a numpy.fill command. Now let's think about making arrays which are not the same value. So the classic one is to use numpy.linspace or numpy.arange, and we'll look at both of those in a minute. Numpy.linspace takes typically 3 arguments. You have a start, that's the 0 here, you have a stop, that's the 1, and you have the number of elements, that's the final one. And we do shift tab here, we can see that you've got start, stop, and then you see it says num equals 50. That means that 50 is the default value. So if you don't specify a number, it will choose 50. So let's just run this. Okay, I should have put in a print b. Okay, so if I run it with 11 elements, you can see that I end up with a spacing of 0.1, going from 0 to 1. And notice that the final element is included. If I don't put in the number here, so I just do 0,1, we end up with 50 and a slightly uglier spacing. So we could get the same result by putting 50 here. And if we decided we wanted the spacing to be slightly prettier, then we could set it to the number of points to be 51, and then the spacing is 0.02. What about this other thing I mentioned, arange? So let's do C is equal to numpy.arange. Now arange takes also a start and a stop, but instead of taking a number of points, it takes a step. So let's say 0.1. And let's run that. And again, I need to print it. Oopsie. And what we see is we've got a step of 0.1, but arange by default misses out the final term. So it does not include 0, the 1. So again, if we do shift tab, I'm actually doing a double tab. So I'm doing shift tab to make the window bigger. And so you see values are generated within the half open interval. That means it includes the starting point, but excludes the stopping point. You might be tempted to use arange whenever you want to use to create values spaced evenly, but you have to be just a little bit careful, and let me show you an example of why. Let's assume that we've defined a step size delta, and in this case I'm going to define it as 0.3 minus 0.2. This is an artificial thing I've done to create this problem, but often you might be creating step sizes by some kind of arithmetical operation. So if I now write c is equal to numpy.arange of 0,1, delta, and I print c, I suddenly get a different answer. I end up with the 1.0 included where before I didn't. Now, why is that? And the reason that is because as follows. If I print delta, you see that it is almost but not quite 0.1. And so what has happened here is that because that delta is not quite what we wanted, the return from numpy.arange is not exactly well specified. So if you're going to use arange to generate a set of values up to a specific endpoint, you need to be awfully careful. Sometimes it's better to use linspace. There are various operations you can do as if you had vectors. So let's create a couple of vectors. Let's say the vec x is equal to numpy.array. Now that's creating a numpy array, and I'm going to pass in one of these lists that we were using earlier, and I'm going to make this a familiar three-dimensional vector. So that's just a sort of a Cartesian x vector. Let's do vec y is equal to numpy.array of, and again we need the extra brackets, 0.0, let's say 1.0, comma 0.0. And now I could do something like vec z is equal to numpy.cross vec x, comma vec y. Numpy.cross for a 3D vector or a 3D array produces the cross product, and again you can check exactly what this means here. And what happens when we do this? Well, let's print out the result. Print vec z. We get 0, 0, 1, and that's good because x cross y is equal to z is the standard result. We could also print numpy dot of, let's say, vec x with itself, and that gives us 1.0 as you would expect. So all of those vector operations are available there. There's a number of different things that you can look at in the notes, which will give you practice questions. There's a couple of other things I just want to show you to do with array stepping and slicing. So let's actually just do a little bit of plotting. I'm going to create an array with a size of 101, and I'm going to create a time array as using numpy.linspace. So I'm going to go from 0 to 2 pi using the number of points. And I'm now going to create the position vector for a particle in circular motion. So let's say the posvec is equal to numpy.array of numpy.cos of t, comma numpy.sin of t. Notice, by the way, the little the brackets are paired for you by the Jupyter Notebook. So you can see that this final bracket here is green and it's paired here with the thing at the beginning. And that tells me that actually I've been silly. I need to say posvec is equal to numpy.array. And you'll notice now that final bracket is red because there isn't a corresponding open bracket. If I just check that, you can see that those open and closed brackets are there. So what this is going to do is it's going to generate an array of cosine values and an array of sine values based on all of these t's. And so let's just run that. Cannot create and construct a d type from there. Yes, I've been foolish. I did need that extra set of brackets, and I put the brackets in the wrong place. So numpy.array, and now I've put that double column of the cosine and the sine inside round brackets there. And if we just check, numpy.array takes an object and a d type, and I was falling into the exact problem I had told you about earlier, which is I was passing it these two things as separate arguments. Now let's try running that again. Excellent, that worked. So now let me show you why I've done that. I just want to plot something. So let's say time is on the x-axis, and I am going to plot the 0 component of the pos vector. And so when I do that, I get a cosine. That's because what I've done is I've created an array here which has 2 rows. The first row is a whole set of cosines, the second row is a whole set of sines, and here when I do posvec of 0, that picks out the first row. If I change it to 1, then I get the sine. So that's picking out the cosine or the sine. We could create the vector the other way round. So let's do that. Let's set this up as follows. So we're going to say that posvec is equal to numpy.zeros of, let's say, n comma 2. So that means I want it to have n rows and 2 columns. And then I'm going to say that posvec of colon comma 0, in other words, all of the row elements and the first column is going to equal numpy.cos of t, and posvec of colon comma 1 is equal to numpy.sin of t. If I do that, what happens if I try and do the command I did before? I get an error, and the error is shown to be in this plot. And then if you look down here, it tells me what the error is. It says x and y, i.e. so you're plotting x against y, t against posvec, must have the same first dimension, but they have shapes 101 and 2. Okay, so we've done the wrong thing. So what we actually need here is colon comma 0. In other words, take all of the rows and only the first column. And now what happens? When we plot it, we get the cosine. Now, we can plot a subset. So this is called slicing. So let's try setting a variable half n, and I'm going to set that as the integer value of n over 2. Why am I doing that? Well, okay, let's not do that. Let's just do the following. Let's say that I want to plot t from 0 up to n over 2. And then, of course, I have to give the same command here for posvec, 0 to n over 2. And I get an error. And the error says slice indices, i.e. this 0 and this n over 2, must be integers. And n, because it's 101, n over 2 is 50.5, so that's no good. So therefore, what we do is we create this half n as the integer value of n over 2. And if I put that in here, 0 to half n, then I plot only the first half. So that's an example of what's called taking a slice. And you can also do stepping. And actually, let me just demonstrate how we do stepping using a slightly different plot. So here what I'm going to do is plt.plot of posvec of colon comma 0. So that's the cosine. And I'm going to plot it against, and that's the x coordinate. And I'm going to do colon comma 1. That's the sine. That's the y component. Oh, I should have meant posvec. So pos isn't defined. And we get, well, it should be a circle, but it looks like an ellipse. And what's going on here? Well, if you look at it, the x-axis is longer than the y-axis. This is standard when you're plotting graphs, but when you want to do something which should be circular, you want to change that. So what we're going to do here is going to introduce a new command, plot.axis, and I'm going to say I want that to be scaled. And when I do that, then it ensures that the y-axis and the x-axis have the same length. Okay, so now let's introduce the idea of stepping. So we're going to define a variable step, and I'm going to set that initially equal to 1. And so what we're going to do is we're going to say we're going to have the position vector. The colon here means from 0 to the last number. Okay, so it's as if I was just doing a 0 colon n. We can put a second colon in and then do step here. And what that means is we want to go from the beginning of the array to the end of the array, but we're only going to take every step elements. Now step is equal to 1, so when I run this, there's no change. Now if I change step to 2, it doesn't look like there's much change, but if you look very carefully, you can see that actually our circle is no longer quite as smooth. If I take step up to 5, that becomes much clearer. You can see that we've actually got an icosagon, a 20-sided shape, and if I change it to 10, then we've got a decagon, a 10-sided shape. So what we're doing is we're just stepping through the points and taking only every 10th point in the array. The final thing that you can play with in NumPy is a way of shifting an array. So what we're going to do is we're going to do plt.plot of t, comma, and I'm going to introduce the command numpy.roll. What that does is it shifts an array and it loops it around as if it were circular. So let me just illustrate this. So we've got posvec of colon comma 0, so that's going to be the cosine, and then I'm going to give it a shift. So how many elements am I going to shift it by? I'm going to shift it by 10 elements. So let me just show you what that does. Okay, so when we do that, what it has done is it's taken the starting element, which was here, and which was at 0, and it's shifted it by 10 units along. So the entire array has just been shifted, and you can play with that shift and see what happens. And if you make it negative, then it shifts in the opposite direction. So what that means is that the element which was at 0 in the array has become now the element at -10. And because Python can count backwards, -10 is equivalent to 91, which is sitting here. So now the element which is at 0 was at 10. This is going to be enormously useful when we come to do numerical differentiation, so you should be happy with how that works. That covers most of what I wanted to talk about in terms of simple NumPy array manipulation. It's really important that you practice these kinds of commands because it's only by practice that you will understand what's happening.